video will provide an introduction to impedances, KVL, and KCL. In the last couple of lectures, we've talked about sinusoids, RMS, and phasors. Recall that once we have a sinusoidal source and we include inductors and capacitors in a circuit, we now will have a circuit that has to be solved using first-order differential equations or second-order differential equations. The way that we get around that is we actually do phasor analysis, or we convert the circuit to the complex number domain, and then once we're in that domain, we can use algebra in order to find voltages, currents, and power. So that's what we're going to do today. We're going to talk about how do you convert the circuit from the time domain to the complex number domain in order to get these values in the sinusoidal steady state. So by the end of today's lecture, students should be able to use phasors to do addition, subtraction, multiplication, and addition, and we started that last lecture. You should be able to find the impedance of resistors, inductors, and capacitors in an AC circuit. And you should be able to transform a circuit with a sinusoidal source into the frequency domain by using phasor representation, and apply KCL and KVL to AC circuits. Before we get started, let's do a simple review of things we've talked about already. The first one, what is the correct phasor polar expression for the effective RMS current in the graph shown with respect to the voltage V of t? So if we look at this figure here, the voltage V of t is the blue line, the current I of t is the red line. What you should quickly notice is that the blue line is a positive cosine, and that the red line is a sine. So based upon the phasor diagram that we've talked about before, we know that if the positive sign is here and the positive cosine is here, then the relationship between those is that a phase shift of negative 90 degrees will get the sign. So that means the answer would be either A or C, because they both have a phase angle of negative 90 degrees. However, the amplitude is 50 for the current source and 30 for the voltage source. Since this asks for the effective or RMS current, that's not going to be 50. Why? Because the effective value, or VRMS, is the magnitude divided by the square root of 2. So 50 divided by the square root of 2 is approximately 5. So the answer would be letter A. Okay, let's try the next one. If Z1 is equal to 24.2 with an angle of 32.3 degrees, and Z2 is equal to 16.2 with an angle of 45.8 degrees, what are Z1 times Z2 and Z1 divided by Z2? So the good news is both of these are given in angle notation, and we're doing multiplication and division, so that is the correct form. Let's find that product first. Z1 times Z2 would be equal to 24.2 times 16.2 for the magnitude, and then we add the angles, 32.3 plus 45.8, which yields 392 with an angle of 78.1 degrees. So we already know the answer is letter B, but let's go ahead and do the second half just to confirm. Z1 divided by Z2 would be 24.2 divided by 16.2. You divide the magnitudes and subtract the angles, 32.3 minus 45.8, so we get 1.49 with an angle of negative 13.5 degrees, which also confirms that the answer is indeed letter B. So now let's do an average value example. This is a review of what we talked about in the last lecture. So the following waveform repeats every 10 milliseconds. So that means that the period is 10 milliseconds. What is the average value, or IDC, of the waveform? So recall there are two ways we can do this. We can use the formula IDC equals 1 over the period, the integral over 1 period, I of t dt. Or remember that the integral is the same as the area under the curve. So what we're going to do this time is actually find the area under the curve. So we're going to have 1 over 10 milli times the area of this first waveform, this first term here, would be 2 milli times 40 minus the area of this second rectangle, 2 milli times 10 plus the area of this third rectangle, which is 2 milli times 30. So when we find that area and we divide it by 10 milli, we get that IDC is equal to 12 amps. So the answer is letter C. So now let's talk about how to write passive circuit elements in the complex number domain or the phasor domain as an impedance. First, let's do a resistor. For a resistor, the voltage and current are in phase. So in the phasor domain, you would see a resistor with the same voltage and I, and notice these are bold-face I's and V's, which means they are phasors now. This is not time domain. And if you made a graph of the sinusoids for a resistor and for the voltage and the current, what you would see is that they are exactly in phase. In this case, the dashed line would be I of t and the solid line would be V of t. As a phasor diagram, which basically means you would then write the voltage and current for a resistor as vectors, what you would see is we have a voltage here, and it has an angle theta, where the magnitude is the length of the vector, and the current would be directly on top of it with a different magnitude, but they would have the same angle. How about inductors? For inductors, the voltage-current relationship is V is equal to J omega L times I. And for the inductor, the voltage leads the current by 90 degrees. So once again, the circuit model is a voltage source and a current source. And now the inductor is J omega L, where omega is the angular frequency. So now if you look at the graph, I have the current, I of t is the dashed line, V of t is the solid line, and it is 90 degrees out of phase, which means the voltage leads the current by 90 degrees. So if I make a sketch of this relationship, what you would see is that if the current is here, and there's the angle theta, then the voltage would be over here, and the difference between those two would be 90 degrees, and this means the voltage leads the current by 90 degrees because it's in front of I. Okay? The capacitor, I is equal to J omega C times V. The current leads the voltage by 90 degrees. The impedance of the capacitor is 1 over J omega C. The circuit model is the voltage and the current. And now the solid line is still the voltage, but I of t is shifted now to the right because it lags behind the voltage by 90 degrees. So if we made a sketch of this, here's the current, there's theta, and the voltage would be down here, and the angle between those two would be 90 degrees. So Ohm's law in the frequency domain would be stated as V equals I times Z. Instead of resistance, we now have impedance because it represents resistors, inductors, and capacitors. Note that impedance, Z is equal to R plus JX. So if you're talking about a resistor, the impedance is R. If you're talking about inductors and capacitors, you use X, where X is the reactance. In all cases, impedance is measured in ohms, and the real part of the impedance is the resistance, and the imaginary part of the impedance is called the reactance, or X. And inductors and capacitors are identified with the reactance, which is why you see we now have J's, J omega L and 1 over J omega C. So to summarize what we discussed in this table, the impedance is R plus JX, where R is resistance, X is reactance. The real part is the resistance. J times the imaginary part is the reactance. So when you have a resistor, the impedance is just R, or the resistance is R. If you have an inductor, the impedance is J omega L. There is no R, and the reactance is omega L. And a capacitor can be written as, notice above we had 1 over J omega C, but that's the same as negative J over omega C. There is no real part, and the reactance is negative 1 over omega C. Now let's try an example of converting a circuit from the time domain to the frequency domain, and then find the voltage across the resistor, the inductor, and capacitor. So here we have a circuit in the time domain. It has a sinusoidal source, 10 cosine 2000 t amps is the current source. Omega is equal to 2000 radians per second. Whenever you have a sinusoidal source, omega is the value that multiplies the t, or another way to think about it is the coefficient on the time element. We have a resistor that's 90 ohms. We have an inductor that's 32 millihenry and a capacitor that's 5 microfarads. So the first thing we want to do is to convert this circuit to the phasor domain. The first step in converting it to the phasor domain is to write the source as a phasor. So the current source would become 10, there is no phase angle, so it's with an angle of 0 degrees, and the units are amps. And then you would write the resistor, the inductor, and the capacitor in the phasor domain. So the impedance of a resistor is the same in the time domain and the phasor domain, so the resistor would still be 90 ohms. The impedance of an inductor is J omega L, or J times 2000 times 32 millihenry, which is equal to J 64 ohms. So you put that on the inductor. And the impedance of a capacitor is negative J over omega C, or negative J over 2000 times 5 micro. Remember, multipliers are very important. So that's negative J 100 ohms. So we put that on the circuit. So since we're looking for voltages, we're trying to find VR, VL, and VC. We can use Ohm's law to do this. We already know that everything is in series, so they all have the same current. So the voltage across the resistor as a phasor would be I times R, or 10 with an angle of 0 degrees times 90, which is equal to 900 with an angle of 0 degrees, and the units are volts. The impedance of the inductor would be I times ZL, which is 10 with an angle of 0 degrees times J64. Remember, J64 is the same as 64 with an angle of 90 degrees. This is something that sometimes confuses students. Because this is the real axis and this is the imaginary axis, J64 would be a vector that points straight up the imaginary axis with a magnitude of 64. That's the same as writing 64 with an angle of 90 degrees, because it has an angle of 90 degrees with respect to the positive real axis. So this would become 640 with an angle of 90 degrees. And the units are volts. The voltage across the capacitor would be equal to I times ZC, which is 10 with an angle of 0 degrees. Now the capacitor is negative J100, so that represents a vector that points straight down the imaginary axis with a magnitude of 100, or that would be the same as 100 with an angle of negative 90. So that becomes 1000 with an angle of negative 90 degrees, and the units are volts. So these would be the answers for the voltage across the resistor, the inductor, and the capacitor as phasors in polar notation. What about the values in the sinusoidal steady state? Let's do that next. VR of t in the sinusoidal steady state would be written as 900 cosine, and you keep omega the same, 2000 t. There is no phase angle, so that would just be volts. VL of t would be equal to 640 cosine 2000 t, and that has an angle of positive 90 degrees, and the units are volts. And VC of t would be equal to 1000 cosine 2000 t minus 90 degrees, and the units are volts. Okay, let's try another example. Here I have a parallel circuit or a single node pair circuit, which means all of these elements have the same voltage. And I have a sinusoidal source. It's a voltage source, 10 sine 100,000 t plus 20 degrees. So for this example, omega is equal to 100 kiloradians per second. So remember, this is the circuit in the time domain. So the first thing I want to do is to redraw the circuit in the phasor domain. So the voltage source is actually a sine. So remember the relationship between a sine and a cosine. If I draw my phasor diagram again, here's my positive sine, here's the positive cosine. So if I have a sine plus 20 degrees, that would be my 20 degrees. That's the same as a cosine minus 70 degrees. So this can be written as 10 cosine 100 kt minus 70 degrees, and the units are volts. So this would be 10 with an angle of negative 70 degrees. So now let's draw the resistor, the inductor, and the capacitor in the phasor domain. Remember, the impedance of a resistor is the same in the time domain and the phasor domain. So the resistor is still 10 ohms. What about the inductor? The inductor would be J omega L, or J times 100K times 40 micro. So the inductor is equal to J 4 ohms. Let's put that on the circuit, J 4 ohms. The impedance of the capacitor would be negative J over omega C, which is equal to negative J over 100K times 1 micro, which is equal to negative J 10 ohms. Let's put that on the circuit. And now we're ready to find the current. Okay, so we're going to label the current through the resistor, IR, the current through the inductor, IL, and the current through the capacitor, IC. So to find the current through the resistor, IR would be equal to the voltage across the resistor divided by the resistance. They all have the same voltage of 10 with an angle of negative 70 degrees. So divided by 10 would be 1 with an angle of negative 70 degrees, and the units are amps. What about the current through the inductor? That would be the voltage across the inductor divided by the impedance of the inductor, 10 with an angle of negative 70 degrees, divided by J4 would be 2.5 with an angle of negative 160 degrees. And units are amps. The current through the capacitor would be equal to the voltage across the capacitor divided by the impedance of the capacitor, 10 with an angle of negative 70 degrees, divided by negative J10 is equal to 1 with an angle of 20 degrees, and the units are amps. So now let's write the answers in the sinusoidal steady state. IR of t would be equal to 1 with a cosine of 100 kt minus 70 degrees, and the units are amps. And what you should see is that this is in phase with the voltage source. In phase means that they have the same phase angle. So it's negative 70 degrees, and the voltage source was also negative 70 degrees. IL of t is equal to 2.5 cosine 100 kt minus 160 degrees, and the units are amps. And what you would see is that this has a phase angle of negative 160. The voltage was negative 70, so the current lags the voltage by 90 degrees, as we said before. And IC of t is equal to 1 with a cosine of 100 kt plus 20 degrees, and the units are amps. And what you should see here is that the current through the capacitor leads the voltage by 90 degrees, which means if this is positive 20 and that's negative 70, this is in front by 20 degrees. Okay, let's try one more example to conclude today's lecture. The magnitude of the reactance of a 10 millihenry inductor and a 0.2 microfarad capacitor are equal when the frequency is what? First, let's write down the impedance of an inductor. The impedance of an inductor is J omega L, which is the same as JXL. So the reactance for an inductor is omega L. The impedance of a capacitor is negative J over omega C, which is J XC. So that means that the reactance for a capacitor is negative 1 over omega C. So this says when the magnitude of the reactances is equal. So that means when the magnitude of XL equals the magnitude of XC, or when omega L equals 1 over omega C. So omega times 10 milli, which is L, must be equal to 1 over omega times 0.2 micro. So if we solve this for omega squared would be equal to 1 over 10 milli times 0.2 micro, which is 500 meg. So omega is equal to 22.36 kiloradians per second. So now our choices are 3.56 kilohertz, 200 megahertz, 22.36 kilohertz, and 21 kilohertz. Notice that all these units are in hertz. Remember, the units for omega are radians per second. The unit for frequency F is hertz. So we don't have the answer yet. So F is equal to omega over 2 pi, which is 3.56 kilohertz. Paying attention to units is extremely important. So the answer is letter A. And this concludes today's lecture on impedance, KVL, and KCL.